This video lecture is meant to cover the information in Chapter 8, Section 2, where we will be using electron dot structures to create what are called Lewis structures, and from that we will be able to determine molecular shapes. You may recall that elements in the first column all have one valence electron and have a electron dot structure that looks like this one. Every element in the second column will have an electron dot structure that looks like this one. 3 valence electrons will have an electron dot structure that looks like this. 4 valence electrons will look like this one. And as you go forward, 5 valence electrons, 6 valence electrons, 7, and 8. So if you take a moment to write down those electron dot structures, you'll need those as we continue on in this lecture. So if we were to take those electron dot structures and start piecing those atoms together to create molecules, we can then show the molecules and what's happening with the electrons overall, the whole molecule, in what is called a Lewis structure. So the first example we're going to take a look at is H2, hydrogen gas. And for this, we need to show 2 hydrogen atoms coming together, each one with a valence electron. I'm going to flip this around so we have the valence electrons facing each other. So what we have here is effectively each hydrogen brings a valence electron, and that's the covalent bond. And so when we have 2 single electrons coming together to form a bond between the 2 atoms, we don't generally draw that as the pair of dots. We typically draw that as a line. And so this right here is what we would consider to be the Lewis structure for hydrogen gas. Very simple. It just has that single bond between them. If we take a look at our second example, O2, well, I'm going to bring over 2 atoms of oxygen, each with 6 valence electrons, and I'm going to turn this one around so these single dots are facing each other. So you can see here that this, or perhaps you can see that this is going to be a bonded pair of electrons, and this is going to be a bonded pair of electrons, but you will have 2 pairs of unbonded electrons around each of the oxygens. And so we would rewrite this as O, double bonded because there's 4 electrons being shared between the 2 atoms. But we do have to indicate that there are non-bonded pairs, and typically we draw them something like this. So this oxygen has a lone pair of electrons up here, a lone pair of electrons here. This oxygen has a lone pair here and a lone pair here, and a double bond in between. And so this is what we call the Lewis structure. If we take a look at N2, I'm going to bring over 2 electron dot structures for nitrogen. We can see here that nitrogen has 3 single electrons around each of the nitrogen atoms. So those 2 are going to bond, those 2 are going to bond, and a little bit tighter fit, those 2 are going to bond. Each nitrogen will be left over with 1 lone pair, but if we rewrite this as a more neat Lewis structure, we would draw this as a triple bond between the 2 nitrogens, and we would then indicate that each nitrogen has a lone pair of electrons around it. I'm drawing the lone pair on opposite ends because typically this electron pair will repel from these electron pairs that are being shared. Next we'll take a look at chlorine. Chlorine has 7 valence electrons, and so I'm going to rotate this one so that the single electrons are facing one another. So if we then indicate where the bonded pair There's the covalent bond, and effectively this becomes the Lewis structure. Of course, you wouldn't write the symbol upside down. So you'd have two Cl's, you'd have a line in between to show the covalent bond, and then each chlorine would have 3 lone pairs of electrons, like so. So that's the Lewis structure for Cl2. Next, we have a water molecule. So here we're going to need to have a single oxygen and 2 hydrogens. So if I bring those hydrogens over like so, right, we can see that we'll orient these so that the single electrons are facing one another. And so if we were to rewrite this molecule, we'd have something like this, with the hydrogens coming off at about a 90-degree angle. It's actually more than that in reality. It's about a 120-degree angle. But what's important here for the Lewis structures are typically written with 90-degree angles, even though the real angles are different than that, as you'll see later on in this lecture. But there are no lone pairs around the hydrogen. There are, however, 2 lone pairs around the oxygen that we do need to indicate. So this is the Lewis structure for water. The Lewis structure for ammonia, NH3. There's your nitrogen with the 5 valence electrons. I'm going to bring in the 3 hydrogens indicated by the subscript. And I'll flip this hydrogen around so we can at least have these single electrons facing one another. The pen and show here there are 3 covalently bonded hydrogens around the central nitrogen. So if you were to rewrite this Lewis structure, you would have a nitrogen with 3 hydrogens coming out, like so, and a lone pair of electrons sitting on top of the nitrogen. Last, we have methane. Methane has a carbon with 4 single electrons. It has to have 4 hydrogens as indicated in the chemical formula. So I'm going to bring around 4 hydrogens around that chemical formula. And we can see here, if we draw the covalent bonds to represent the 2 shared electrons between each pair. If I were to rewrite this molecule as a Lewis structure, I would have a carbon with 4 lines coming out of it, and on the other end of those lines I would have a hydrogen and there are no lone pairs around either the hydrogen or the carbon. So it's these are very simple Lewis structures. In a more advanced chemistry class, you would approach making Lewis structures in a slightly different fashion. But for our purposes, it's just a matter of sticking together the various atoms as if they were little pieces of Lego. Well, there is something referred to as VSEPR theory. VSEPR is an acronym that stands for valence shell electron pair repulsion. Because electron pairs will repel each other, that will dictate the shape of molecules dependent on how many electron pairs there are in a molecule. Electron pairs, also known as covalent bonds, will arrange themselves in space around an atom in a way to be as far apart from each other as possible. So covalent bonds, which consist of 2 electrons, are all going to push against each other because they're made up of negative particles and they just want to be as far apart from each other as possible. So VSEPR theory is the theory that describes the shape of various molecules. Now there are lots of different shapes. You're going to be responsible for just these 5. There's a linear shape, which may be more easily represented by this drawing. There's a bent shape, that might be drawn this way. Trigonal planar. Trigonal because it kind of forms a triangle. Planar because all four of these atoms are in the same plane. There's a trigonal pyramidal, which is again a triangle, but there are four atoms. The center atom is kind of stuck up in space higher than the other outer three, hence the pyramid in the name. And so this might be one way to diagram it, not very artistically, however. And then the last shape is tetrahedral. Tetra means four. There are four atoms bonded around the center atom, as you can see here. And it forms what was called a tetrahedral. So these are the 5 shapes of molecules that you'll be held responsible for and determining from molecular formulas and model kits that you'll be playing with in the classroom to see how molecules are arranged. So this concludes the material found in section 3 of chapter 8, having to do with VSEPR theory. And if we go back a little further, we started out today by talking about electron dot structures. So electron dot structures lead into showing Lewis structures of molecules, which Lewis structures can also then lead into determining shapes of molecules. That's it. See you in the classroom.